would act on the mass to give us W. W is your weight, and W is equals to mg. Does that make sense? Now, there is also always a force acting upwards, anybody seated, especially for a baby. For instance, a baby may be seated for some time, but later, probably after 2 seconds, the baby will topple over. The baby will fall either to the front, using the head to hit the ground, or to sideways. The baby actually has a force that can keep the baby upright. That force is normal reaction, but the baby don't know how to put the force to work. Does that make sense? And that's why the baby is falling. But for us who are adults, we have weight when we sit, right? Because our mass is acted upon by gravity. Does that make sense? So, but we have the sense to apply this upward force. That upward force is called your normal reaction, right? The normal reaction. So this normal reaction is always present for every human seated. But for baby, they might not possess it, and that's why they fall. So, but we know now that we have normal reaction. And that normal reaction is also a force equals to mg. So in other words, it means that R, for this kind of case now, for instance, R is equivalent to W. It means that if the mass of block given, if the mass of block given is 5 kg, for instance, right? So what I'm just going to do here is I will say 5, which is my mass, times 10. That is your acceleration due to gravity, right? So that's 10 meters per second square. So we have 15 newtons, right? So the same thing applicable here. If I apply it, so I will get 15 newtons, provided that the acceleration due to gravity is 10. Does that make sense? Sometimes it's be 9. In short, the standard is 9.8, right? So this is the first case. So the first case, what are you picked out of the first case? If I have a force dragging an object to a side, opposite the force must be frictional force. Down the object sitting on any plane, whether smooth surface or a rough surface. If it's a rough surface, this is what I will just do. I will just draw a line here to show that the surface is rough. That's the difference between the smooth surface and the rough surface. Does that make sense? So now note that between this block and the surface, right? Between the block and the surface, let me have this green substance. Oh, it's not really strong on that. Okay, let me have the screen, right? So between the surface, this block and the surface, there is a surface here. In between the two is something we call coefficient of friction, mu. Something we call coefficient of friction. Does that make sense? Coefficient of friction tells how much frictional force you can have. The higher the coefficient of friction, the higher the frictional force. Does that make sense? So don't forget the frictional force is equals to mu r. Does that make sense? All right. So it means that from this diagram, I can derive 2 formulas from this diagram, and the 2 formulas are gotten from the second equation of motion. Second equation of motion. So the second equation of motion is giving you F equals to mass times acceleration. Does that make sense? The force is called a net force. When we say a net force, we mean total force on a particular side or on a particular plane. Does that make sense? So to take the net force, so for me to form the first equation, which is number 1, For me to get the first equation, I need force to be equals to ma, right? So for a body that is not moving, that is not accelerating, does that make sense? For instance, this body now, it is not accelerating. Do you get it now? These force are assumptions that if the force drag an object towards a particular side, then the frictional force will be opposite it. Does that make sense? But if the question tells you that the body is accelerating, then what happens? You have, if the body is accelerating, then you have F equals to ma. Does that make sense? So, and don't forget that your F is your net force. So for the net force, you are to subtract the forces on this plane like this horizontal plane. Does that make sense? You have to subtract the forces. So what are the two forces we have there? We have the frictional force minus the normal force, which is force of motion, equals to ma. So these two forces here, the frictional force and the normal force, are still representing this force, because it is, this force tells you a net force. Does that make sense? All right. So that's my equation 1. But if the body is not moving, that, in other words, if the body is not accelerating, what happens to A? So for a body, so this condition, this is your equation 1, right? So for a body, for a non-accelerating body, what happens? Fr minus F is equals to m times 0, because acceleration is assumed to be equals to 0 for a body where you know that your acceleration A is equals to 0. Does that make sense? So in that regard, Fr will be equals to F, because the whole of this is going to end up giving you 0, right? So everything is going to give you 0. So you end up having this for your horizontal plane, right? So the second formula you can derive from there is also your R, your normal reaction, and your weight. This is showing you vertical. This is showing you vertical side, vertical forces. Does that make sense? So it's still boiling down to your Fr, your R to be equals to your F equals to ma still, right? So since acceleration, the object is not moving up and down, right? It's not moving vertically. What happens? M times A will be equals to 0. So your F there is telling you R minus W, right? Or W minus R. W minus R is still the same. So what do we have here? We're going to have W to be equals to R. In other words, W is always equivalent to R. So this is your second formula for that case 1. So can we quickly move to case 2? Case number 2. Case 2 is telling me, I hope you're writing. Case A is telling me, no, let me make it case 1B. Case 1B. Case 1B. All right, question.
So that accelerating body, does it also mean a moving body? Like when they give us a question like the body is moving,
a moving body.
Should we also use MA?
Yeah, they are going to. You said?
Should we also use MA? Like
for
FR minus
a body
for, and that is moving.
Of course, you are going to use it as MA for a body accelerating, because in the question they are going to give you the acceleration of the body.
Okay.
Do you understand now?
Yes, sir.
All right. So we have case number 1B. Case number 1B, let's assume we have a body lying on a plane, whether a horizontal, a rough plane or a smooth plane, right? Between the body and the surface, between the body and the surface lies your coefficient of friction. Don't forget this component. In short, once you're dealing with diagrams, one of the first thing you do is to bring out your components, right? So I know that for this mass, let's assume the mass is okay, I don't want to assume a value for the mass, but I know there is a mass here, right? So probably a block, right? A block of mass. So here it should be your normal reaction. Here should be your weight. Here, provided the body is drawn. But this is what I want to do for this body now. This body, we are assuming that a kid that loves playing, dragging a toy, is dragging this toy or the block of mass at an angle, right? So this is the force of the boy, right? So the boy must be dragging it to an angle, and that angle can be any angle. You can be given any angle. So we can have theta as the angle. So in that case, for us to have the force, this force cannot be like this. So what are we going to do? We have to resolve the force to two sides, vertical and horizontal. So resolving that force vertically and horizontally, what am I going to have? I'm going to have F cos theta here as the horizontal force. So what am I going to have for this other force as the vertical force if I'm going to resolve it here, right? Because this force here, we are resolving it because it's falling in between x-axis and y-axis, and it can be like this. So what am I going to have here? I'm going to have F sine theta, right? If that is the case, once you resolve, note that once you resolve this force, the force disappears. The force is no more or would no longer be in use. Does that make sense? So in that regard, what am I going to have here? So if the force, don't forget the force was initially here, right? So if the force is no more there, what are we going to have? We are still going to have the object in that direction, in this same direction, because the force, the boy is dragging it towards the side, right? So what will be opposite it? It will be your frictional force. Don't forget your frictional force is still equals to mu r, right? But this r here is not equals to W because this r here is not equals to W. In the previous case, we got to know that W is equals to R, right? From this case here, W is equals to R. But in this case here, W is not equals to R. The reason is this. The reason is this. Here, we know that R can be any value and W can be any value. Let's assume W is 50 newtons and R is also 50 newtons. But don't forget that here now, let me take off this force so that we will know that we are not dealing with it, right? So here now, you don't have only R as your vertical component facing W, because W must be equals to everything upwards here, everything upwards here. So in other words, we must have W equals to R plus F sine theta. We are adding it because they are forces acting in the same direction. They are acting upwards, right? So this one, W is always acting downwards towards the center of the earth, right? So in that regard, if you have this to be equals to this, since it's an equation is a body, is a mathematical expression in which the two sides must be equal. So this place can be 49 plus the whole of this can now be 1. Does that make sense? Right? So that makes it 50 plus 50. But if you have it that R is 50 and W is 50, then you're saying that 50 equals to 50 plus this f sine theta would certainly have a value, even if it is 0.00000000, anything you assume it to be, right? This side is still bigger than this side, which makes it not to be an equation any longer. Does that make sense? So to make these two sides equal, R must not be equals to 50, just like W, right? So in that sense now, this R will have a problem, will not be exactly 50. Does that make sense? All right, so can I get the equations we are supposed to have here? Can we have the equations written? So what are we going to have? Don't forget your second Newton's law of motion, right? Second Newton equation of motion, rather. So you have number one. For the first equation, take the horizontal plane first, right? So we are going to have F equals to ma. Don't forget, this is still your net force, right? So this is your net force. You can subtract the two forces on the two sides. So we are going to have F cos theta equals to ma. So for a non-accelerating, this is a general statement, right? But for a non-accelerating body, what do you have? For non-accelerating body, what are you going to have? You're going to have Fr minus F cos theta, right, equals to ma. But the A acceleration here now, for a non-accelerating, acceleration is always equals to 0. So that will be times 0. So the whole of this is going to give you 0, right? So hence Fr can be equals to F cos theta, right? So this is your first part of the equation. Now, the second part of the equation, that's of this same diagram, we have the vertical axis, right? The vertical axis is still telling you F equals to ma. So don't forget your net force. You're going to have W minus into bracket of R plus what? F sine theta, right? And that will be equal to ma. So if A acceleration is equals to 0, what are we going to have? We're going to have A times 0 is times 0. So that means that this is going to be giving you 0. So we still have our W pod minus into bracket of R plus F sine theta, right? In that sense, what are we going to have? We are going to end up having W to be equals to R plus F sine theta, right? That will form my equation 2. Is equation 1 for this case, equation 2 for this case. It's quite simple, right? So, and this is what I'm going to have. So note that once you observe that your question is a non-accelerating body, let me give you a shortcut. Once you observe that your question is a non-accelerating body, that is, the body is not accelerating, you are not giving acceleration of the body in the question, what you just have to do is simple. Just equate the vertical axis to the bottom to the top. You just say W is equals to R plus F sine theta. You've gotten one of your equation. Then you have Fr to be equals to F cos theta, right? So these are the two equations you need very quickly to solve the question. All right, that is that on that case. So I'm treating all the cases. So once we get a question, we'll know the case to quickly attack, right, with. We'll know the formula to quickly attack with. So I'm moving to the case of an inclined plane. The case of an inclined plane. So I have case 2. Case 2 is an inclined plane. Case 2 is an inclined plane. So we have here. So I have a body. This is a body here. So I'm looking at this as trailer, right? Let's assume this is a trailer, and the trailer is having the trailer is this. So this is the floor of the trailer. The trailer is carrying a sand. So the trailer is carrying inside of it. The trailer has a load, and the load is sand, right? So let's assume this is the trailer. The trailer is carrying this load, right? So this is the floor of the trailer. So this is the head of the trailer and the legs of it, right? So, but I'm not going to show all of that here. Now, if this trailer wants to offload this load, do you understand now? Being sand, the trailer don't need anybody to start entering into it and bringing out the goods, since it's not a fragile substance, right? So the trailer can just press the hydraulic, right? The hydraulic press. Once the driver press the hydraulic press, what happens? This whole of this will start to increase in size. It will start to increase in size. So what will you observe? Don't forget, before the pressing of the hydraulic button, let us know that before that, the normal reaction still remain intact here, right? Your weight still remains here. Depending on where the force is, the force can be here. If the force is here, the force of motion, then the frictional force will be here. But let's pause a bit about the force and the frictional force. It depends on the direction the person is pulling, or the trailer is going to offload whatever thing it's carrying. So what we're going to have here, if the trailer now open up like this using the hydraulic button, what happens? This particular line here, this particular flow line here, the one I just deleted, is going to increase from that point to, it's going to increase like this, right? Showing an inclination pattern, right? So this load here, this load is going to be like this. It's not going to be flat again, right? It's going to be like this in the quest of pouring down. So we have this load bending, right? So it has bent like that. So let's assume the load is still there and the load is about falling, right? The load is about falling. So don't forget that as this guy has opened the hydraulic press, the back of the trailer has opened, what happens? There is an angle that will be formed between the floor of the trailer and the opened part, right? So this sand can now easily drop, right? So what is actually dropping the sand? What's actually dropping the sand? It's if it gets to this point. If it gets to this point, the sand particles might not still drop until probably it's open more. But let's assume that the sand particles are not dropping, or probably they are in between, dropping and not dropping. So if it would actually pour down, what is actually bringing it down? We don't know for now, right? But we know that this weight still remains intact here. This scenario, probably I should draw another diagram to show all of that. So let's have this. All right. So I don't want to complicate the diagram. So I have this. This is the load now. Right. This is the load. Okay. This is fine. So by opening, what happens? This, we have theta here, right? So, and this is the load in it. Don't forget that the weight of the load, despite it has opened, despite the trailer has opened up, the weight of the load does not change its direction. The weight of the load still remains at this position as W, right? But something will happen to normal reaction. You know, normal reaction R for a normal body that is not bent, normal reaction. This is the normal reaction. So this is my normal reaction R up there. Because the load, the stuff has bent towards this part like this. It has bent towards this part. Normal reaction is going to change its direction. The direction also supposed to affect W, but W would not change because W is the weight of a body, and the weight of the body does not change with direction. It is always pointing to the center of the earth, right? So if you are if this load happens to be a man, if the man is bent like this, you observe the man trying to hold himself not to fall down like this, right? So, but the weight of the man will still be to the center of the earth, will still be to the center of the earth. Man might decide can fall down, the man can still try to stand upright, then the weight still, if the man stands upright, the weight comes here, it's still pointing to the center of the earth, it won't change. But if the man falls down, the total weight will be around this place, right? So irrespective of how the man is standing, the weight will still point to the center of the earth, and that is why we're not changing the position of this W. But R is going to change. What will happen to R here? R will change to B R here. Now, that tells us that R is undergoing a kind of shift. R is supposed to be equals to W, right? R is supposed to be equals to W, but R is not going to be equals to W any longer. That is why I am using a dotted line, a broken line, right? This is the initial position of R, with moving straight, just like this, moving straight with W. So, but R is no more there. R has now undergo a kind of slant change due to the opening of this body. So what has happened? What has actually happened there? So what has actually happened there? R is no more there. But R must be equals to something. R must be equals to something, right? R must be equals to something, just as it was equals to W initially. It must also be equals to something, but we don't know that thing yet, right? So note that this side, I'm drawing a line here like this. I'm drawing a line here like this. This side, for an inclined plane does not take this part as x-axis. Do you understand now? And does not say this part is y-axis, because the body has changed its direction, and because the body has changed its direction, every other thing is going to change. So this part is going to be, instead of this part being y-axis now, like the R and W being y-axis, they are not going to be y-axis because their direction, the direction of the R has changed. What's going to happen? What's going to happen? This part is going to be your x-axis. this part is going to be your y-axis. So this means that the whole of this r to the whole of this r down here is your down to this place is your x-axis. So we have our x-axis here. X-axis here. Does that make sense? This part is going to be my y-axis. So I am working with this x because I am saying this part is also x because they are parallel. Does that make sense? They have the same sides. So this part is y-axis. So anything that goes like this here now, I'm going to take it as my y-axis. So this part is going to be my y-axis. This is my y-axis. All right. Can I take this off now since I've located my y-axis and x-axis? So W still remains here, but we want to make the W suit the plane, right? We don't want the W to remain here. We want it to suit the plane, and also want it to suit the R. We want it to work in line with the R, just like a normal friction will have, just like this will have, right? So, but and more so, the reason we'll be doing this is because the weight of this object that is sitting on the inclined plane would not just be on a side again. You observe that this body can easily slide down by itself even without pushing it, especially if the surface of that is as smooth as the surface of the plane too, right? This object can just slide down. Nobody is touching the object. It's just if you put a baby on a slide, the baby, you don't need to push the baby. The baby will just slide down by itself. So what's pushing the baby down? What's that pushing it? It is the weight of the baby, right? So, and if the weight of the baby is pushing it down, it means that for this body too, there is something bringing it down, and that thing is weight, right? But what kind of weight it is, we don't know yet. So, but also this guy here is going to be equal to a particular weight, right? And we can only get those weights if we resolve this weight to vertical and horizontal axis. Horizontal axis, I mean, is x-axis. So we can have W sine theta, and here we can have W cos theta, right? Because we are resolving it to y-axis and also to x-axis. I've said it earlier, but whenever you want to resolve to y-axis, use sine, and to x-axis, have your cos. Now, note that due to that same opening, an angle is open here. Due to the opening, the angle is equal to this angle. Some textbook might actually put another angle here. They are just telling you opposite angle, and they are all equal. The three angles are all equal. So, if that is the case, and we move forward.
Yes.
All right. So this is what we're going to have. Now, note that if actually this weight is sufficient, the weight is acting downwards like this. If actually the weight is sufficient to bring this object down, if the weight, that's a conditional statement. If the weight is sufficient to bring this body downwards like this, right? Then opposite the weight would be your frictional force. Right? This ends our study for case 2a. This end our study for case 2a. So based on what we have for this plane now, we can easily derive our formula. So we have, for number one, we have F still equals to M, right? So if F is equals to MA, what are the forces we have on y-axis? For this plane, we have W sine theta and we have FR. Don't forget your FR is still equals to W mu R here. It's still the same. So we are going to end up having W sine theta minus FR, everything equals to MA. If the body is not accelerating, provided the body is not accelerating, that is where acceleration is equals to 0. What are we going to have? We'll have W sine theta equal to FR, because the whole of this will tend to what? Will tend to 0, right? So this is my first equation. So I have for the inclined plane. So I have equation to derive equation 2. What am I going to have? Consider the R and W cos theta. So your x-axis part. So we have R is going to be equals to W cos theta, provided acceleration is equals to 0, right? That's the condition. I am not starting from F. I didn't start from F equals to MA, right? So that is that on that inclined plane. Any questions so far before I move to the same inclined plane, but I want to give you another condition, the condition of us having a force pushing the object downwards or pushing it upwards through that same plane. All right, can we have questions?
Sir.
All right.
When the body is moving,
okay,
so will it be R minus W cos theta equals to MA, or W cos theta minus R equals to MA?
Will it be R minus W
Cos theta?
No, the W, you've resolved the W. Yes. So it is assumed that the W no longer exists there. Do you understand? Once you resolve a body, you assume that the body is, you're not seeing the body any longer, and that is why W is not equals to anything, right? Because you have resolved it. Does that make sense?
Yes, sir. Like, my question is that since you said R is equals to W cos theta, provided that A is equals to 0, that is for a non-moving body.
Right. Okay.
So if it is a moving body, will it now be R
if it's
minus...
a moving body?
Yes.
Yeah, it's going to be R. In other words, if it's a moving body, you're going to link it up to F equals to MA, right? It should be R minus W cos theta equals to MA. So they are going to give you this acceleration, right?
Yes, sir.
But note that if for an inclined plane, if acceleration is going to be given, right, the body will not be moving vertically like this now. Do you realize that?
Yes.
The body will be moving on the plane like this, right?
Yes.
Hence, it means that acceleration cannot be given here. So it will still be R equals to W cos theta.
W cos theta.
Do you understand that?
Yes, sir.
All right. So, any other question? Any other question? All right. If there be no question, can we move to the next case? Can we move to the next case? We have case 2. This case 2 is case 2A. Case 2A. So can we take case 3 now? Case 3 now. Case 3, I said case 3. Case 2B. Case 2B. Case 2b is the same thing as case 2a, but with a little change or a little condition surrounding it. So let's have this here. I have a body, I have a plane, right? Inclined, right? This is an inclined plane, right? So we have the whole of this. Okay, this is the inclined plane. Now, don't forget your constants. Constant number one. So your constants, don't forget your constants. You have W here, right? Don't forget your R will be bent, right? You have your R. Down here is an imaginary line showing that it is not actually equal until you resolve W. So you're going to have W cos theta, right? So then I have here, if I resolve it to the y-axis, I'm going to have W sine theta. This is always a constant. Note that W sine theta here is a constant. It is the weight bringing the object downwards. The weight bringing an object downward cannot fall here. Don't make that mistake, right? The weight cannot fall down here because weight will always be tending towards the floor. Does that make sense? In any condition you are dealing with, in any situation you are dealing with an inclined plane, you must not put your weight here. It is wrong, right? Because the weight cannot be acting upwards like this, right? It acts downwards. They act downwards. So if that is the case, can we have a condition now? What's the condition I want to put now? Let's assume that somebody, normally if the weight is sufficient to bring this object down, right, the frictional force supposed to be falling like this, right? But now I am seeing the weight not being able to, or let's say I'm seeing an obstruction to the weight, and the obstruction is that somebody is now pushing the object, is trying to push the object like this towards this part, right? So if the person is pushing the object like that, it means that your force in motion, this force is trying to put the body in motion in order to push the body up the plane, right? So hence, what will happen if force in motion is involved and the force in motion is to this direction? Something will happen, and that thing is that frictional force would come to this part, because frictional force, from the definition of friction, frictional force must be opposite force in motion. Does that make sense? So, which means that there are two components who are facing downwards, and a component will try to push this object upwards. Do you understand now? So what does that denote? It means that for anybody to be able to push this object up the plane, the person must be able to overcome, number one, the frictional force, number two, the weight of the object, before the person can push it downwards. They can push it upwards, rather. Right. So what is that telling us? Don't forget your angle here. Your angle is theta. Your angle can still be here, theta, right? So what's that telling us? Formula-wise, it means that we will have equation 1 to be still F equals to ma, right? That's second equation of motion. Your F is telling you your F will be equal to FR plus W sine theta. I added the forces because these two guys are together. Do you understand now? And they are facing the same direction. They're acting in the same direction. So I'm going to have minus, what's opposite them? Your force, your normal force, F, right? So your F is opposite them. The totality of everything is going to give you equals to MA. So if acceleration is equals to 0, that's condition. If the acceleration is equal to 0, what are you going to have? You're going to have FR plus W sine theta equals to F, because the whole of this are going to tend to 0, right? So this will be my first equation. Don't forget your FR here is always equals to mu R. Does that make sense? All right. Then your second equation, where you have the x-axis, is always R equals to, R will always be equals to W cos theta, cos theta, cos theta. Note, this is my second equation. Note that whenever your coefficient, normally you are supposed to be given coefficient of friction. Coefficient of friction is that which is between the block and the surface. And I told you that the higher the coefficient of friction, the higher the frictional force between the block and the surface as it slide down or slide up, right? So if you're not given the coefficient of friction, know that your coefficient of friction is always equals to tan theta. Tan theta. So any value of theta you're given, just look for your coefficient of friction using tan theta, right? So that is case 2B. Any question? Any question before I move further for case 2B? Question?
Sir.
All right.
In that case, case 1B.
Case 1B.
Yes.
Case 1B. All right, this is case 1B.
So for the mu, if it's not given, can we also use tan theta?
For the mu, if mu is not given, yes, you can also use tan theta.
Okay. Also for case 1A too.
Exactly. Case 1A don't have case 1A don't have.
Okay, don't have. Okay, we can use it for case 1B.
Case 1B. So for case 1A, if you are not given for case 1A, what you should just do, just have FR equals to your mu R. So you will be given, you will have your mu to be equals to FR over R. Does that make sense? Right, that's correct, right? So can we have the next case, which would mark the last case for tonight? So go and brainstorm on these cases. In our next video, we're going to have the last. We're going to have questions on all of the cases, including the last one. So I'm going to deal with case 2B now. Case 2B. So I have case 2B. Right. So for case 2B, I have right, I have this. I have this plane, right? Right? So I have this whole of this, right? So, and I have my angle here. All right. So I have the whole of this. Now, what would I'm going to have here is that I'm going to give a condition. A condition. Let's assume this block on the slide here supposed to slide down, but it probably the frictional force between the block and the surface is high. Does that make sense? And the stuff is trying to come down gradually, but you don't want it like that. So you want to push it so that the movement can be fast. Does that make sense? So it means that you are going to apply a force in motion, and the force in motion is going this way, is going downwards this way. So you are having F force going downwards this way, right? So if that is the case, what are you expecting? If force is going downwards this way, hence your frictional force is not going to be downwards here, right? Because frictional force must be opposite your force in motion. So what are you expecting? You are expecting a force here, a frictional force opposite motion. So you can see that the direction of the frictional force, when you compare it with what we have initially, you observe that the direction of the frictional force has changed. So it depends on this. The frictional force is here now, but for this case, the frictional force has changed its direction due to the direction of the force applied. Does that make sense? So for the first case, you have a force not applied. No force is applied here, but we are assuming that the weight is the one bringing the body down. Does that make sense? So in the real sense, what we do there is that we make the frictional force to be opposite that weight bringing it down. So for this case, you can see what is playing out here. So what does that mean? It means that two forces are acting downwards. The first force is the frictional force, and the second force is your weight. Then it's opposite this particular frictional force, right? This is your normal force. This is your weight, right? So hence equation 1, we can have our equation 1 to be equals to W sine theta. I'm still using F equals to MA, right? So W sine theta plus F minus FR, everything to be equals to MA. If acceleration is equals to 0, what is going to happen? We are going to have W sine theta plus F, everything equals to FR. That is acceleration is equals to 0, right? So, and that is my first equation. So the second equation is going to be R to be equals to W sine theta. W sine theta. So these are the two equations we are going to have for this case. So this is my first equation. This is my second equation. So ensure you revise all of this before tomorrow. Then we'll be taking questions. Probably I should try to solve a question today. Then just use it to practice and have
W sine theta.
What's that?
Because
Any question?
W equals to sin theta.
W equals to
Let me see. How is it equals to W cos
Toib.
theta now?
Toib, what I say? Oh, thank you. That's R is W cos theta. Thank you. That's an error. So we have R equals to W cos theta.